this as my dot product in order to evaluate the directional derivative. Since I'm evaluating towards the point log 2 and log 3, let's plug in numbers directly to make our evaluation more direct. Okay, so what I'm saying here is instead of computing the dot product and then plug in number, I can plug in number right here and evaluate the gradient vector directly. Are with me? Mm-hmm. Okay, so this is going to be, if I plug in log 2, log 3, I'm getting an e2 minus log 2 minus log 3. So this requires a bit of the knowledge for operations involving exponentials. Right, so this is e2 minus log 2 times e2 minus log 3, right? So e2 minus log 2 is exactly 1 over e2 log 2, which is just 1 over 2, okay? So here is the computation here. So the exponential is minus e2 minus log 2 minus log 3. First of all, I can break this exponent by using the product rule of exponentials, right? This is equal to e2 minus log 2 times e2 minus log 3. Are you with me? When you compute the two exponentials, you're adding the exponents. So this is exactly what I have here. And also, if I have a minus in the exponent, this is equal to minus 1 over e2 log 2. And multiply by 1 over e2 log 3. e2 log 2 is exactly 2, right? Here is the explanation. What is this number? This number is the number that if you raise this as your exponent to the base of e, you're getting a 2. Am I right? The explanation, the definition of log 2 is this is exactly the number. If you plug in this number into the exponent, you're getting a 2. That's the definition of log, right? Therefore, if I plug in this number right here, I'm getting a 2. Similarly here, the exponent log 3 is exactly defined as the number. If you raise it to the e, you're getting a 3. So this is a minus 1 over 2 times 1 over 3, which will give you 1 over 6. So both of them are.
Doesn't the negative actually distribute?
Which one?
For the second step?
The second step?
Yeah.
Well, you can understand this as a plus minus 3.
Yeah, but then isn't the whole thing, it's multiplied by negative?
Oh, the negative sign is after you product. This is all multiplication, right?
Mm-hmm.
This is all multiplication. This is minus 1 times this factor times this factor. It doesn't distribute, right? They only distribute if you have multiplication and addition, right? Again, this is not the key point for calculus. This should be the topic for probably pre-calculus. I just to remind you of how to make these exponentials to operate. So I have a minus 1 over 6, 1 over 6. So it's going to be minus 1 over 6 times 2 over square root of 5 minus 1 over 6 times 1 over square root of 5. So how many 1 over square root of 5 do I have? So it's 2 over 6 and 1 over 6. I have minus 3 over 6. So it's going to be minus 1 over 2 square root of 5. So this is going to be the directional derivative of the function over there in the direction of 2 over square root of 5, 1 over square root of 5 at the base point log 2 and log 3. Okay? Questions? Okay, so we can interpret this again as a slope of tangent line to a curve as the intersection between a plane containing this vector and the surface defined by the function. Right? This can be defined as a slope of tangent line. And also, this slope is minus. We know at this point, following this direction, the function is decreasing. Right? Function is decreasing. If the slope is positive, as what we have somewhere before, we can talk about on this curve is the intersection following the direction the function is increasing. So this can be interpreted as whether the curve is increasing or decreasing. Okay, so right now I want all of you to be able to compute 3 things. If the vector to talk about the direction is not a unit yet. You can normalize it. Second, you should be able to compute the gradient vector. And third, you should be able to use the dot product between these two vectors to compute the directional derivative. And then you should be able to understand, at least convince yourself, what these numbers or the functions are talking about. These numbers are talking about a slope or rate of change. Okay? Okay, so here is the question I want to ask you, which is the question for the whole lecture today. I still have one function. Z is equal to f of x1. So at its base point, AB. Okay? So here's my question. If I'm sitting on my base point AB, I shoot up, I get this point on the surface. Okay? So if I change my base point AB in different directions, in every direction I have, I will have a rate of change. All right? I will have a rate of change given by the directional derivative over there. So different directions will give me different directional derivative. Yes? Mm-hmm. So if I have a direction in x, I might have a number as my slope. If I have a direction in y, I have a number as the slope of the tangent line. So in different directions, I might have different rates of changes. Now my question is, in which direction I will achieve the maximum rate of change? And in which direction I will achieve the minimum rate of change? Okay, so this is a very, very trivial question and a very natural question you can ask yourself, especially if you go to military, you want to design a strategy of going to different directions. You're in the mountain, there are different directions. In every direction you go, there's a steep and there's a more better route you can go. So these are talking about a rate of change. So on the top of a mountain, if you go to different directions, there are some steeper way you can go. There's our, how should I say that? Less steeper way you can go, okay? And this steeper or less steeper way of going into different directions are exactly talking about a directional derivative. So I want to ask the question, what is the maximum value of this directional derivative and what is the minimum value of this directional derivative? Okay, so the maximum rate of change is talking about steepest as something. I want to make sure my English is correct. A S C P N T. Okay, and the minimum rate of change is talking about steepest descent. Okay. So a practical question you can ask yourself is, according to this method of computing the directional derivative, if I want to achieve the steepest ascending, I want to get to a higher point as fast as possible, I need to find a direction where it will achieve the maximum rate of change. If I want to go down as fast as possible, I need to find the minimum rate of change or the smallest value of the directional derivative. Are we clear? So this is the very natural question you can ask yourself. Now we already defined the directional derivative. Actually, we have the definition in a very mathematics strictly form. It is equal to the dot product between two vectors. Okay? We need our knowledge of the dot product. How do I define the dot product in the geometric form? It is equal to length of the gradient vector multiplied by the length of the other vector, then multiplied by the cosine value of the angle between these two. Okay? So as long as I can write in this form, immediately I don't need to worry about this middle value, because U is always a unit vector, right? It is just talking about direction. We already agreed. We have to make sure this is of unit length. So this is just equal to gradient of f multiplied by cosine theta. Again, I'm asking in which case I will achieve the maximum value of this directional derivative. In which case I will be able to achieve the minimum value. And it's completely depending on the theta, which is the angle between the directional vector and the gradient vector. you will achieve its maximum value is maximum when theta equals 0. So when theta equals 0, you will achieve the maximum value, and it is exactly equal to the length of the gradient vector. All right, because cosine 0 is equal to 1. So the maximum value for the directional derivative is the length of the gradient vector, and that is essentially why we want to compute this gradient vector. Because from the formula, you can use the linear combination with no problem at all. A gradient vector contains a very, very crucial information. Okay, so this is the whole point of calculus. Computing very easy, but you want to interpret it in a very meaningful way. The gradient vector contains the very important information. It will be, the length will be the maximum rate of change. Not only that, imagine if theta is equal to 0, u is exactly in the same direction of the gradient vector, and I want to normalize this u. So how should I choose my directional vector to achieve its maximum value? So it is denoted as u max. It should be in the direction of this guy, and it should be of unit length. So naturally, it is equal to gradient of f divided by length of the gradient. Okay. So this is the question I want you to be able to answer. Okay, so I'm gonna say it again. So base point AB, I can move in 360 degrees. There's one direction I will achieve maximum rate of change, and that direction is given by the gradient. Okay, and if I wanna write down the directional vector in this direction explicitly, it is just equal to normalize the gradient vector. And in this direction, I can achieve the maximum rate of change, and that rate is equal to the length of the gradient vector. Are with me? Okay. So du of f is minimum when theta equals pi, 180 degrees. Then you will get a cosine pi equals minus 1. And then in this case, my directional derivative is equal to minus gradient of f, and u minimum is in the opposite direction, minus gradient of f divided by gradient of f. Okay? So these information are all contained in the textbook. If you don't, if my formula is not clear enough to you, okay? Maybe I should make this much more clear. So the direction I want to achieve is u minimum is equal to minus gradient of f divided by length of gradient. So these are the two extremely important information for this lecture. Again, I said this multiple times. Computing part of the derivative is the skill you have to practice, but being able to tell some information out of them is more related to the graph and the geometry. Okay? So if you're sitting at this point, you want to go high. You want to increase your function value. The direction you want to move to in order to get high as quickly as possible is to move in the direction of the gradient vector. If you want to decrease the function value as quickly as possible, you want to go to the opposite direction. Okay, you want to go to the opposite direction, function value will definitely decrease, and it will decrease in the most fastest way. Okay? Okay, I can also propose another question. As long as I choose theta equals 0, theta equals pi, I can also choose some other special value. Theta equals pi over 2, cosine value vanishes, directional derivative is going to be equal to 0. In other words, if I choose my directional vector to be orthogonal to the gradient vector, then the rate of change will be exactly equal to 0. Okay? So this is another information you can say. So when theta is equal to pi or 3 pi divided by 2, so directional derivative of f is equal to 0, or this is talking about the rate of change is equal to 0. When theta is equal to pi over 2 or 3 pi over 2. So in this case, u is orthogonal to the gradient vector. Okay, so that's the geometric meaning of the partial derivative or the directional derivative vanishes as long as you go in the orthogonal direction of the gradient. The function value will not change at all. Okay. So let's practice one question, and then I want to look at this case more carefully. Okay. The first two cases are pretty straightforward. So let's say if I have a function, which is still pretty simple function, 2x squared minus y squared minus 3. So at the point p 2 minus 2, I want to find the maximum and the minimum of duf, and also I want to find the direction where I will achieve the maximum or minimum directional derivative. Again, throughout the semester, all the computations are easy, but you have to be extremely clear what you're computing. Okay? Even without beginning my computation, I know when I want to find the maximum or minimum directional derivative of a function at a point, I'm getting a number and a number. And when I'm looking for the directions where I will achieve these two numbers, I'm looking for a 2-vector and a 2-vector. Now with me? A vector and 2-vector. And if you already know the properties of the directional derivative, the maximum and minimum are opposite numbers. All right? You can achieve the maximum as the length of the gradient, minimum is the negative length of gradient. U max is the normalized direction in the gradient vector, and U min is the opposite direction. Okay, so these are hand by hand. And also, when you know it is a vector in 2-dimensional space, you have to write down it explicitly with 2 components. All right? So be very clear about what you're computing here. So gradient of f. Here is a very no-brainer beginning. As long as you see the irrational derivatives, you compute the gradient vector in the very beginning. Right? The gradient vector will eventually come up. You have to use it anyway. So as long as you see this kind of a directional derivative, just compute your gradient vector in the very beginning, because you will be using this eventually. So gradient vector is equal to